Have you ever wondered why transition metals like iron and copper show such vibrant colors and multiple oxidation states, unlike the more predictable S-block elements? The secret lies in their electronic configuration, the way electrons arrange themselves inside atoms. In the case of D-block elements, the last incoming electron doesn't go into the outermost shell, but rather into the d orbital of the penultimate shell. That's why we call them N-1 D-block elements. Their general configuration is open bracket N-1 close bracket d raised to 1 through 10, followed by NS1 or 2. This means that the d orbitals are progressively filled as we move across the series, while 1 or 2 electrons enter the outermost s orbital. This configuration gives rise to their characteristic behavior, from variable oxidation states to forming colored ions and complex compounds. And that's not all. These elements span 4 horizontal rows or periods, the 3D, 4D, 5D, and the relatively unexplored 6D series. They form the central backbone of the periodic table and of inorganic chemistry itself. Let's begin with the 3D series, the first row of transition metals starting from scandium with atomic number 21 to zinc at 30. Their electronic configurations ideally follow a straightforward pattern. The 3D orbitals gradually fill while the force orbital holds 1 or 2 electrons. For example, scandium is written as argon core followed by 3D 1 force 2 and titanium as argon 3D to force 2. By the time we reach zinc, we have a full 3D 10 and force 2. But nature loves exceptions, and here, 2 elements stand out, chromium and copper. Chromium is expected to have 3D 4 force 2, but instead, it chooses 3D 5 force 1. Similarly, copper skips the expected 3D 9 force 2 and opts for a more stable 3D 10 force 1. These anomalies aren't accidental. They reflect a deeper energetic preference, which we'll now explore. Why do chromium and copper break the expected pattern? The answer lies in stability. Atoms tend to prefer configurations that minimize energy, and half-filled or fully filled subshells provide a special kind of symmetry and stability. In chromium, filling all 5 3D orbitals with 1 electron each results in a symmetrical, low-energy arrangement. Hence, 3D 5 force 1. This also maximizes what we call exchange energy, a stabilizing effect caused by the ability of electrons with the same spin to exchange places in degenerate orbitals. Copper follows a similar logic, preferring a completely filled 3D subshell, 3D 10, even if that means reducing its 4 electrons to just 1. This configuration stabilizes the atom due to minimal electron-electron repulsion and enhanced exchange energy. So, while these exceptions may seem odd at first glance, they're actually a glimpse into how nature optimizes atomic structure at the quantum level. Now let's take a closer look at the order in which orbitals are filled. According to the Aufbau principle, electrons occupy orbitals of lower energy first. In D-block elements, the 4s orbital has slightly lower energy than the 3D orbital, so it fills first. That's why scandium, with atomic number 21, has an electron configuration of argon, 3D1, 4s2. However, once we start adding electrons to the 3D orbitals, their energy decreases due to increasing nuclear charge, often making the 3D orbitals lower in energy than 4s. Now here's the twist. Although 4s fills before 3D, it also gets ionized first, meaning during the formation of positive ions, the outermost 4s electrons are lost before 3D electrons. Refer to the energy level diagram on screen. You'll see that after 4s is filled, 3D begins to drop in energy, highlighting the dynamic nature of orbital filling. Understanding this trend is essential when predicting the behavior of transition metal ions in redox reactions and complex formations. Let's move beyond the 3D series. The 4D series begins with yttrium, atomic number 39, and ends with cadmium number 48. These elements follow similar patterns, with electrons filling the 4d orbitals after the 5s orbital. Yttrium, for instance, is krypton core 4d1, 5s2. Then comes the 5d series, starting with hafnium and ending with mercury. But this series has a twist. It's interrupted by the entire lanthanide series, which fills the 4f orbitals between lanthanum and hafnium. This f-block insertion adds complexity to electronic configurations, but also explains many of the unique physical and chemical properties of these heavier elements. Most 4d and 5d elements follow predictable trends in configuration, but again, exceptions do arise due to increasing nuclear charge and other relativistic effects, which we'll discuss next. Have you ever wondered why gold appears yellow instead of silver like most metals? Or why mercury is a liquid at room temperature? The answer lies in relativistic effects. In very heavy atoms, like those in the 5d and 6d series, inner electrons move so fast that their mass effectively increases, a consequence of Einstein's theory of relativity. This causes the contraction of s and p orbitals and expansion of d and f orbitals. As a result, electrons in the 6s orbital of gold are pulled closer to the nucleus, stabilizing that orbital and altering the expected configuration. That's why gold shows a configuration of 5d10 6s1 instead of 5d9 6s2. These effects influence more than just electron placement. They explain color, conductivity, bonding strength, and even why platinum group metals are so chemically inert. So, relativistic effects aren't just theoretical curiosities. They shape the real-world behavior of some of the most valuable metals known to humankind. Let's quickly revise what we've explored. We began by understanding the general electronic configuration of d-block elements and how they involve the progressive filling of n-1 d orbitals with 1 or 2 electrons in the outermost ns orbital. We then dove into the 3d series, highlighting the famous exceptions, chromium and copper, and understood how half-filled and fully filled d orbitals provide extra stability. We also explored the filling sequence and orbital energy levels, using the Aufbau principle to decode why force fills before 3d but gets ionized first. Then, we moved on to the 4d and 5d series, noticing how the lanthanides insert themselves into the 5d pattern. And finally, we uncovered the fascinating world of relativistic effects in heavy elements, which change not just electronic configurations, but also the physical and chemical behavior of elements like gold and mercury. I hope this session helped you appreciate how atomic structure influences everything from ion formation to color to industrial reactivity. Until next time, keep observing chemistry not just in books, but all around you, in metals, machines, medicine, and materials. See you in the next topic.